Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about enthalpies of formation. So a good way to view enthalpies of formation, these are probably one of the most reliable sources for the enthalpy of an individual chemical species. So when we're talking about enthalpies of formation, what they really are is it's going to be a reaction enthalpy to form 1 mole of the target molecule in the specified phase from its elements in their most stable state at 25 degrees C. So for example, if I'm making ammonia, I'm making it from nitrogen, whose most stable form is going to be nitrogen gas, and hydrogen, whose most stable elemental form is hydrogen gas. Now, one of the things to make note of is since I'm producing 1 mole of the product species, you'll often find that the reactants it's being generated from have some kind of odd stoichiometries, in this case, 1/2 and 3/2 respectively. And so to generate if I'm going to generate 1 mole of ammonia, this will end up producing about 46 kilojoules of energy. Now, whenever you're looking at an enthalpy of formation, always make sure that you have the right corresponding reference elements. So when we're looking at carbon, that's going to be solid carbon in the graphite state. I know diamonds are pretty, but graphite is the most stable form of carbon. Hydrogen, we're looking at hydrogen gas. Nitrogen and oxygen, nitrogen and oxygen gas. Again, diatomics are very common for the right side of the periodic table, metals for the left, as demonstrated by sodium being the most stable form of sodium, and chlorine being the most stable in the gas phase. So watch out when you hit bromine and iodine. Bromine is the most stable in the liquid phase, and iodine, most stable in the solid. So again, make sure you know exactly what the most stable forms of all the common elements are. So using these as our base reference points, we can figure out exactly how much energy would be produced or consumed to generate a host of commonly available chemical species. And it's worth noting, if you know where to look, you can find the standard enthalpies of formation for almost any commonly used chemical species, whether it's carbon monoxide or methanol or ethanol or any of your your halide acids. So whatever you're interested in, you can usually find the number. Now, one of the things I do want to make note of is most enthalpies of formation tend to be negative. So things like carbon monoxide and carbon dioxide. This means that these molecules are relatively stable. If you've ever seen a positive value, so for something like any of the nitrogen oxygen combinations, most of these have positive enthalpies of formation, meaning that it takes energy to make them from nitrogen and oxygen gas. If you see these positive values, most of the time they're considered as relatively unstable molecules. That said, watch out because there can be a certain misnomer. Values tend to get both more positive and more negative as the molecule gets larger. So for example, as I go from propane to butane, we see a decrease in the enthalpy of formation, meaning it's more favorable to make butane. But part of this is the fact that any hydrocarbon tends to be more stable than carbon and hydrogen, and you're using more carbon and hydrogen to make bigger molecules. So sometimes it's less about the stability of the product, it's more about how unstable the reactant molecules are. So this is what enthalpies of formation are. But one of the big things we care about is how can enthalpies of formation be used? So in a sense, we can use our standard enthalpies of formation in a very similar fashion to Bond Disassociation Enthalpies. If we know the energy of our reactants and products, we can use this to we can use the difference of these values to figure out the enthalpy of the entire reaction. So let's go ahead and take a generic reaction. A molecules of A plus B molecules of B make C and D. So when we're doing this, we're going to have to sum up all of the enthalpies of the products. So this is going to be all of D and all of C, and then subtract out the enthalpies of the reactants. Now, one of the things to make sure you note when you're doing this is make sure that you have the exact number of molecules of each times their respective enthalpies of formation. So for example, the enthalpy of formation of C will be the enthalpy of 1 mole of C. However, in this case, I'm making C of them. So I'll have to multiply all the values by the stoichiometric coefficients. And again, as always, products minus reactants. So when you're doing this, I want to make sure that you note that this is going to be the energy for 1 mole of reaction, not 1 mole of reactant or 1 mole of product. So in this case the enthalpy of reaction would correspond to producing C moles of product C, or consuming A moles of my reactant A. So again, make sure that you remember that this will be the enthalpy per mole of reaction, not per mole of product or reactant. So when we're looking at how we're using these enthalpies, one of the good ways we can think about this is what I'm doing is I'm figuring out how much energy it would take to take my reactants and break them down into their base elements, because that's really what what taking the negative of the enthalpies of formation would be. The sum of the enthalpies of formation of the products, however, is going to be how much energy I get from taking those elements and recombining. So in general, if the enthalpy of your reactants is greater than the enthalpy of your products, you'd expect the overall reaction to have a positive enthalpy, and this means the system will be endothermic. I'll have to add in extra energy into the system to make up that difference. If I'm looking at if the enthalpies of my products is greater than the enthalpies of my reactants, that means I get a little left over. I get to take some loose change home, and that's going to be how much heat goes out into the environment. So let's go ahead and look at how we can use our enthalpies of formation to look at a real reaction. So let's look at something very environmental. It turns out that the combustion of coal often produces sulfur dioxide. The sulfur dioxide, once it gets in the atmosphere, can combine with water vapor and ozone to produce sulfuric acid. So this is one of the principal components of acid rain. Now, this also can have some influence because it can end up generating some heat. So let's figure out exactly how much heat is generated. So for this, we're going to go ahead and start by taking the sum of the enthalpies of our products. Well, that's easy because I only have sulfuric acid. So I can take the enthalpy of formation for sulfuric acid, but remember, there's 3 moles of it. So 3 times the enthalpy of formation of my sulfuric acid minus, and now I'm going to subtract out each of my reactants. 3 moles of sulfur dioxide, 3 moles of water, and 1 mole of ozone. Now let's go ahead and put numbers to those values. So one of the things you'll note, since all of these enthalpies since the enthalpy of formation of water and sulfuric acid are negative, when I add these in, I'm going to be adding those values. However, ozone is a quite unstable molecule, so it has a positive enthalpy of formation, so the negative sign does not cancel out. So I can then go ahead and add up all of these numbers, and it turns out that this reaction has a negative enthalpy, so this reaction is going to be exothermic, by 830 kilojoules per mole. So it turns out this reaction is highly exothermic. And as a result, it can actually cause some disturbances if you let ozone and sulfur dioxide get into areas. It can cause uneven heating and has been known to, when it happens in bodies of water, cause a little bit of problems that way too. However, one of the things I want to make note of, so far we're looking at just the enthalpies of formation for species in the gas phase. Same principles can be applied for a liquid or solid. However, we're going to have to look at things a little bit differently once we get to the aqueous phase, because it turns out that electrolytic solutions behave a little bit differently. So next time, we're going to finish up the course by talking about enthalpies of solution. Until then, take care.